Hi, welcome to this lecture on Quicksort. Here's an outline for the lecture. We'll first talk about the basic Quicksort algorithm, and then we will consider some algorithmic improvements. And finally, we'll compare Quicksort with the other sorting algorithms that we have seen so far. Quicksort, just like merge sort, is a divide and conquer algorithm for sorting, and it works by partitioning an input array into two subarrays and then sorting the subarrays independently. Here's a quick example on how the Quicksort algorithm works. So let's say our input is what is shown here in the first line. It simply consists of the strings Q, U, I, C, and so on. In the first step of the algorithm, what we do is we take that input array and simply shuffle it, okay? And that is what is shown here. So this line here is simply a shuffled copy of this input array, all right? And then we perform the partitioning step. So that involves picking the first element of the input array as what we call the pivot element. And the partitioning step simply partitions the input array about the pivot element. And what that means is once the partitioning is done, the pivot ends up somewhere, and the elements to the left of the pivot are all smaller than or equal to the pivot, and the elements to the right of the pivot are all greater than or equal to the pivot. Okay, so that's what the partitioning step does. And then we simply repeat the process. We sort the elements to the left of the pivot, which are all these guys, recursively. Okay, and when we do that, we simply end up with a sorted version of that. And then we sort the right half, the right part of the pivot, meaning all these elements. So we simply call Quicksort on the elements to the right of the pivot, which will eventually get us a sorted copy of that. Okay, and now if you look at all these elements, they are in complete order. Okay, so that's how the Quicksort algorithm works. It simply partitions the input array into two subarrays and then recursively sorts the subarrays. All right, and in each partitioning step, what we do is we pick the first element of the input array as the pivot element, and then we find the right place for the pivot, and we also make sure that after the partitioning step, the elements to the left of the pivot are all less than or equal to the pivot, and the elements to the right of the pivot are all greater than or equal to the pivot. Okay. So that's how the algorithm works in principle. Now let's look at the implementation. So the Quicksort algorithm is implemented inside of this program called Quick. Okay, and it's implemented as a public sort method, which is static, and this method takes an array of comparable objects. All right. And the first thing that it does is the shuffling step. So it takes that array A and simply shuffles it by calling the static method shuffle inside of std_random, right? And once that is done, the public sort method simply calls the private sort method, which is right here, giving it the array A as the first argument. That's the array that we want to sort, and then 0 for low and A.length -1 for high. All right. And it's the private sort method that implements Quicksort, and it is recursive in nature. Right? So let's go through this method. Since it's recursive, we need a base case, and the base case simply says that if high is less than or equal to low, return to the caller. All right? So either when high is exactly low or when high and low have swapped sides, we simply return to the caller. That's the base case. Otherwise, if you're not at the base case, what we do is the partitioning step. Okay, and that is done by making a call to a private helper method called partition that we will look at later. And partition takes 3 arguments. It takes the array A that we want to sort, and then it also takes 2 pointers, low and high. Okay, and what partition will do is it will simply partition the elements in A from low to high, All right, and what that means is it will pick the first element, okay, in this segment as the pivot and partition the rest of the elements about that pivot such that the elements to the left of the pivot are smaller than the pivot or equal to the pivot, and elements to the right are greater than or equal to the pivot. Okay, and partition will also end up returning the final index of the pivot element, which we store in the variable j. Okay, so once the partitioning is done, j is basically the index of the pivot element. All right. Okay. And then all that we need to do is call quicksort recursively on the elements to the left of the pivot. So the pivot element is at j, and what this recursive call does is it simply sorts the elements to the left from low to j minus 1. So that's the left of the pivot. And then we make another recursive call to sort the elements to the right of the pivot, which is j plus 1 all the way up to high. So that's the right of the pivot. Okay, so it's very simple conceptually. We first partition the elements in A from low to high by making a call to partition, which will pick a pivot element and make sure that it ends up at the right place, and it returns the index where the pivot ends up, which is j. Okay, and then we simply make two recursive calls to sort the elements to the left of the pivot, low through j minus 1, and then we make a recursive call to sort the elements to the right of the pivot, which is j plus 1 through high. Right? And notice that once a pivot is placed at the right place, it never moves throughout the course of the algorithm. All right, so that's something to keep in mind. So that's the implementation of quicksort. So let's first look at a trace of the sort method, the private sort method, right after the call to partition. Okay. So here we have an array that consists of 16 strings, which are these guys, Q, U, I, C, K, and so on, right? So here n, the size of the input array is 16. Okay, now the first step is to shuffle that array. So we simply take that input and shuffle it. So let's say this is what we get after the shuffling, right? And then what we do is we call the private sort method, and the private sort method first partitions the input, which means it picks a pivot, which in this case is k, and then it finds the right place for k, okay, which is given by the index j. Right? So j is 5 because k has ended up right there at index 5. And the partition step guarantees that the elements to the left are less than or equal to the pivot, and the elements to the right are greater than or equal to the pivot. Okay. And then what? And then it's the recursive call to sort on the left of the pivot, which is all these elements. And what does that do? Well, that ends up picking this as the pivot. Okay. And then the partitioning step finds the right place for it, which is this, given by the index j equals 3. And notice that the elements to the left of it are all less than or equal to e. Elements to the right of it are all greater than or equal to e. And then we call sort recursively on the elements to the left of the pivot. And what does that do? Well, that partitions it by picking this as the pivot, finding the right place for it, and notice, that place is given by j equals 2. Elements to the left are all less than or equal to that, and there is no element to the right of it, right? And then we again recursively call sort on the elements to the left of the pivot, which is A and C. That ends up picking A as the pivot, and it finally ends up in this position given by j equals 0. And again, notice that after that partitioning is done, elements to its right are greater than or equal to it, and there is nothing to the left of it. Okay? And then we simply call sort on the left and the right, but there is nothing to the left. There is just this one element to the right, which is placed right there. Okay, and then we do something similar on the right hand side. So we call sort on the right hand side of the pivot k, okay, which ends up picking this guy as the pivot, and then it places the pivot at some location which is given by j equals 6 here. So that's the final place of the pivot, and notice that all the elements to the right are greater than or equal to that pivot, and there is nothing to the left of it. And then we recursively call sort on the right hand side of the pivot. There is nothing to the left, so nothing happens on the left. And what does that do? Well, it picks p as the pivot, and a partitioning step places p at the location j equals 9, which is this guy. And notice these two guys are less than or equal to p, all these guys are greater than or equal to p. And then we call sort recursively on the left and the right, and the call to the left is going to partition this array by picking this as the pivot, and that pivot ends up at j equals 7. And we call sort recursively to its left and right, nothing to the left, but on the right we just have this one element which ends up there. Okay? And then on this side we repeat the same idea, call sort on the right of p, that ends up picking t as the pivot, and t via the partitioning step ends up in this position which is given by j equals 13. Notice that the elements to the left of t are smaller, elements to the right are greater than or equal to the pivot. Okay? And then we repeat the same to the left and to the right. On the left we pick that as the pivot, and after the partitioning step that pivot ends up there, which is given by j equals 12, and the elements to the left of it are less than or equal to it. There is nothing to the right, and then we call sort recursively on this on the left hand side of the pivot, which ends up picking this as the pivot, which ends up there given by j equals 11, and then we call sort on the left hand side because there is nothing on the right hand side, and that just ends up there. Okay, and then the same thing is repeated on the right hand side. This is picked as the pivot. It ends up in this position given by j equals 14, and then we there's nothing to its left. We end up calling sort on the right hand side of this pivot, which ends up placing x there. All right, so we are done with the sort algorithm, and as you can see we have the final result, which is the input array A completely sorted. All right, and notice that once a pivot finds its place, it never moves. So k found its final place right there, and it never moves. It stays at the index 5. All right, let's look at another example. So L, or actually a better example would be something like this. So P found its final place here at index 9, and it never moved. Okay, so once the pivot finds its place in the array, it does not move throughout the algorithm. Okay, so what is the partitioning procedure doing? Well, what it does is it simply rearranges the array such that the entry AJ, okay, is in its final place. So that's the pivot. So AJ is in its final place in the array for some value of j. Okay, so the pivot ends up at AJ for some j, and these two conditions are guaranteed. No entry in A low through A of j minus 1 is greater than AJ. So we have AJ there, and then we have A low all the way up to AJ minus 1, and then on this side we have j plus 1 all the way up to A high. So what we are saying is that in this condition we are saying that none of the elements here are strictly greater than AJ. Okay, so none of the elements is strictly greater than AJ, and on the right hand side none of the elements is strictly less than AJ. Okay, So that's what we are saying in these two conditions. In other words, what we are saying is that after the partitioning step, all the elements to the left of the pivot are less than or equal to the pivot, and all the elements to the right of the pivot are greater than or equal to the pivot. Right? So now let's look at the partitioning procedure, the partitioning method. So it is implemented as a private helper method called partition inside of Quick. Okay? And what are the arguments to partition? Well, it's an array of comparables, A, that's the array that we want to sort, and 2 pointers, low and high. So partition is responsible for partitioning this segment, low through high, in the array A. Okay? So I starts at low, and I starts at low, and J starts at high plus 1. So I and J scan the array from the opposite ends. So I goes this way from low, and J goes that way from high plus 1. All right. So I scans the array in this direction, J scans the array in that direction. And then here we are getting the pivot element. So we say that the pivot element V is simply A at low. All right. So it's basically the first element of the segment that is being partitioned. Right. So V is the pivot. Okay, and then we have this while loop that says while true, which is going to be always true. So we want to make sure that somewhere here we break this loop. So what's going on here is that in the first while loop, we check if A at plus plus I is strictly less than B. Right? So as long as A at plus plus I is strictly less than B, we keep going. Okay, so in other words, what we're saying is if you're looking at an element that is strictly less than the pivot, then we continue. All right, but once we find an element that is greater than or equal to the pivot, then we break out of this while loop. All right, as long as we are looking at an element that is strictly less than pivot, we just keep going. We keep incrementing I. And as we do that in the body, we need to check if high runs over the edge. So since we are constantly incrementing high, it's possible that I might at some point reach the value high, in which case we need to break this while loop. So that's what we have here. Right? So in this loop, we are simply going left to right and stopping when we find an element that is greater than or equal to the pivot. Okay? And then in this while loop, we scan from this side. So J goes right to left, and we stop this while loop when we find an element that is greater than or that is less than or equal to the pivot. Okay, so it's so we simply look for an element that is less than or equal to the pivot. Okay, and when that happens, we break out of this while loop. And notice here again, since we are constantly decrementing J, we need to check if J becomes equal to low or not. When J becomes low, we break, because low is like the you don't want to fall off on the left hand side. Okay. Alright, so from this side, we look for an element that is greater than or equal to the pivot, and from this side, we look for an element that is less than the pivot, right? And then we once we have found these indices, we need to check if if I is greater than or equal to J or not. And if this is true, that means that I and J have crossed sides, right? And in which case we break this while loop. Right, so this break will break this outer while loop, right? And that happens precisely when these two pointers cross sides. But if they don't, then what we do is we simply swap the values at I and J in the array A. So what it means is you found an I somewhere here, let's say, and you found a J somewhere here, right? So they've not crossed sides. So I is still strictly less than J. And what are we saying? So when something like this happens, what we are saying is that the element at I, this element here, is greater than or equal to the pivot. Okay, and this element here is less than the pivot, right? And what that means is that they are on the wrong side, right, with respect to the pivot. So they need to be exchanged, and that's what this exchange does. So it simply takes these two values and exchanges them, right? So it takes A at I, A at J, simply exchanges them. That's what this line does. Okay. Once the exchange is done, the two elements now are on the right side with respect to the pivot. Huh? All right. And then once we get here, what happens is all that we need to do is simply exchange the values at low and j in the array A. So what we are so when we get here, j is basically where the pivot needs to be, right? That's the final resting place for the pivot. So all that we do via this exchange is take the pivot element, which is at low, right? So that was this guy here, and simply put it at index j, and whatever is in j goes to the index low, right? So this exchange is basically what is responsible for placing the pivot element at the right place, which is given by index j, which is the value that is returned by partition. Okay, so what partition does is it finds the right place for the pivot element, which is given by j, and it also makes sure that the elements to the left of the pivot are less than or equal to the pivot, and the elements to the right of the pivot are greater than or equal to the pivot. All right? And the position of the pivot element, the final position, is returned. So let's look at a trace of the partition method. So here is the input array after the shuffle, right? And what does the partitioning step do? And so let's say we want to now partition this array, right? So what does the partitioning method do? Well, it picks the first element as the pivot, okay? And then what it does is it simply scans from left to right and right to left, right? So the first scan is from left to right. So what we are trying to do is we are scanning in this direction, and we stop when we find an element that is larger than the pivot. Okay, so when we do that, we stop right here at R. Why? Because R is greater than the pivot. All right, and then what we do is we scan from the right, looking for an element that is less than the pivot. Okay, so S is greater than the pivot, O is greater, X is greater. When we come to C, we realize that it is smaller than the pivot. Okay, so we stop that scan from the right. So what are the values of I and j at this point? I is 1, j is 12. And what do we do? Simply exchange their values. So that's how that C comes here and this R goes there. Okay? All right, and then we continue. So we scan first left, starting from A. So, and we stop when we find an element that is larger than the pivot. So A is smaller, T is larger. So we stop. From this side, we scan starting at Q. Q is larger than the pivot because Q is bigger than K. M is also bigger than K, but I is smaller than K. So what do we need to do next? Exchange. So that's how this I comes here, and this T goes there. Okay, and then the same procedure again. We scan left, so we keep so E now is smaller than the pivot. L is larger, so we stop, and then from the right, U is larger than the pivot, P is larger, but E is smaller. Okay, so we stop. And we exchange the two. So this E comes here, this L goes there. All right. And then we scan again. So now we stop at this L here from the left, and from the right we stop here. But now notice that I has a value 6 and j has a value 5. So 6 is greater than or equal to 5. So what do? We break out of that outer while loop and we perform the final exchange, which is exchange the value in a low, which is which is k, with whatever the value in j is, which was e. So the pivot, which was in low or 0 in this case, comes there, and e, which was in index 5, comes there. Okay, so that's how the pivot ends up in its final place, in this case at the index 5. Okay? And notice that all the elements to the left of that pivot are smaller than or equal to the pivot, and all the elements to the right are larger than or equal to the pivot. Okay, so that's how the partitioning step works. So what's the running time of the Quicksort algorithm? Well, Quicksort uses approximately n log n comparisons and as many exchanges. All right, so in the average case, the running time of Quicksort is linear-arithmetic. It's n log n. Okay, but in the worst case, Quicksort uses approximately n square comparisons. And when does that happen? Well, that happens in the worst case, which means when A is reverse sorted. All right, so when A looks something like that visually, so it is reverse sorted. In this case, when you have an input like that, which is reverse sorted, Quicksort degrades or degenerates to a quadratic time algorithm. All right, because when we partition such an input, right, in each partitioning step, the first element is picked as the pivot, and every other element is on the wrong side with respect to the pivot, so they have to be moved to the other side. Okay, and you have to do that pretty much for every single choice of pivot. Okay, and hence the algorithm becomes a quadratic time algorithm. Okay, but to get around this, what we do is the shuffling. Right, so it's that shuffling, the random shuffling, that protects against this case. So once we get our input for Quicksort, the first thing that we do is to shuffle that input, and that takes care of this problem. All right, so that's what guarantees that. So it's the shuffling that guarantees linear-arithmetic performance. Okay. So Quicksort is also an optimal sorting algorithm, just like merge sort. It is linear-arithmetic, and that's the best that you can do with comparison-based sorting algorithm. Right? And Quicksort doesn't have the drawback that merge sort suffers from, meaning it doesn't have any additional space requirements. All right. So in that sense, it is better than merge sort. So it is linear-arithmetic in terms of its time complexity, and it doesn't need additional space that merge sort needed. Right? So what are some of the improvements that we can perform with the Quicksort algorithm? Well, one easy way to improve the performance of Quicksort is to use insertion sort for tiny arrays. Okay, this is similar to what we did with merge sort. The implementation that we discussed has this for the base case of the Quicksort algorithm. We simply return when high is less than or equal to low. But we can very easily modify this base case and rewrite it as such, where we say if high is less than or equal to low plus m, simply call insertion sort, all right, to sort the segment from low to high in the array A. Right? So when arrays become smaller than some specified size m, we simply use insertion sort. So this way we don't pay the price of recursion, right, for small arrays. And the typical values for m is between 5 and 15, right? So when the arrays get down to this size, then we simply sort those arrays using insertion sort. Another easy way to improve the performance of Quicksort is to use what is called the median of 3 sorting. And what that involves is we simply sample some items, usually just 3 items. So we pick 3 items at random and pick their median as the pivot. Okay, so just randomly pick 3 elements from the array and pick their median as the pivot, instead of picking the first element all the time as the pivot. Okay, so when we do it this way, by picking the median of a small sample of items, we do better. All right. So those are a couple of improvements. There is another improvement that you can make. Now, and this works very well when you have arrays that have a large number of duplicate entries. All right? So for example, if you're sorting a large personal file by the year of birth, you're going to have many duplicates in your data. Okay? When that is the case, then what we want to consider is an idea due to a very famous computer scientist by the name Dijkstra, right? And that idea is called Threeway Quicksort. And in that approach, what we do is, instead of considering 2 partitions, we consider 3 partitions of the input array, right? And so what are these 3 partitions? Well, one for the items which are smaller than the pivot, one for items that are equal to the pivot, and finally one for the items that are larger than the pivot. Okay, so you have 3 partitions. You have a partition that contains the pivot element. Let's call it V. That's the pivot element. And then the partition to its left consists of elements that are smaller than the pivot, and the partition to the right consists of elements that are larger than the pivot. Okay. And then what we do is, after the partitioning step, we simply call the modified quicksort algorithm on this partition and on this partition. Notice that we don't call it on this partition, the middle partition, okay? Because all the elements here are in the right place, so they need not be moved around, okay? And this modification works really well when your input has large number of duplicate keys. And here is the implementation of this idea. It is called Quick Threeway. Okay, and it is implemented as a public sort method, which makes use of this private sort method, right? So the public sort method simply takes an array of comparables and it calls the private sort method, giving it A as the first argument, 0 for low, and A.length -1 for high. So if A has n elements, this is n -1. So what do we do here? Well, this is a recursive method. So we have the same base case as before. If high is less than or equal to low, we return to the column. Otherwise, we create 2 variables, LT for less than and GT for greater than. LT starts at low and GT starts at high. So they go in the opposite direction. And then we say V is the pivot element, which is the first element in the segment, A at low, right? And then I also starts at low. And then we have this while loop that is responsible for the partitioning. Okay, so this is the partitioning step. So what are we doing here? So as long as I is less than or equal to GT, okay, we compare the element at I with the pivot. So that's given by CMP. Right? So say CMP is A at I dot compare to V. And this is possible because A is an array of comparables. Right? So we are comparing the value A at I with B, the pivot. And if A at I is smaller than the pivot, then this is going to be true. So in that case, what we do is we exchange the values at LT and I in A and simply increment both LT and I by 1. Okay? Note that LT and I traverse in that direction and GT traverses in that direction. So what we are saying here is that if the value that you're currently looking at is smaller than the pivot, then simply exchange the values at LT and I and increment both by 1. Okay? Otherwise, if the value A at I is strictly greater than the pivot, then we simply exchange the values at I and GT, and we don't modify I remains at its current value, whereas GT is decremented by 1. Okay? So that's what we do when A at I is larger than the pivot. And if A at I is same as the pivot, then all that we do is increment I by 1. Okay? And once this while loop is done, what we have is something like this. We have created 3 partitions of the input array. Okay? What are these partitions? Well, the middle partition has the pivot element V. So every value here is the pivot equal to the pivot, right? And then what do you have here to the left? This has values that are less than the pivot, and this partition here has values that are greater than the pivot. Okay, so that's what is done by this while loop. And then once the while loop is done, the partitioning is done. So all that we need to do is recursively sort the first partition. So notice that this sort is from low to LT minus 1. So we go from low to LT minus 1. And then this is LT, the middle partition starts at LT and goes all the way up to GT. And the second recursive call is on the third partition. So that's from GT plus 1 all the way up to high. Okay. Notice that we don't call sort on the middle partition, right? Because all the elements here, which are equal to the pivot, they're all in the right place. They need not be moved around. So sort only needs to be called recursively on the first partition and on the third partition here. Okay? So that's how the quick three-way algorithm works. So let's look at a trace of this algorithm. And we're going to consider the trace right before the recursive calls to sort. Okay? Meaning right after the while loop, the partitioning. All right. So here's our input array with these values, and notice there are lots of duplicates. Okay? So the distinct keys here are just R, B, and W, right? And N is 12. We have 12 elements. Okay. So LT is at 0 and I is at 0. So we are. So how do we do the partitioning? We compare A at I, which is R, with the pivot, which is also R. And they are the same, so in that case, I is simply incremented by 1, so it becomes 1. So now we compare A at I, which is B, with the pivot element. Well, B is smaller than the pivot, so what do? We simply exchange the values at I and LT. Okay? So this guy comes here and this guy goes here, and both I and LT are incremented by 1. So LT becomes 1 and I becomes 2. Okay? So now we compare W with the pivot R. So keep in mind that the pivot V is R. So W is compared with R. W is greater than R. So what do we do in that case? We simply exchange the value at GT, which is this guy, with A at I. So this W goes there and this R comes there. And in this case, only GT is decremented by 1. So GT goes from 11 to 10, and the rest of the guys remain the same. Okay, so now we are looking at I equals 2, so which is this guy, and we compare that with the pivot. They are the same, so in that case we simply increment I by 1, so I goes up to 3. Now we compare this W with the pivot. It's larger, so what do? We exchange it with GT. Okay, so that B comes here, and this W goes there, and GT is decremented by 1. It becomes 9. Okay, so now we compare this B with the pivot. It's smaller, so we increment I by 1, and we increment LT by 1 as well. But before that, we do the swapping. Okay, so we simply swap the values at LT and I. Okay, so this 3 ends up there, and this R ends up there. Okay, and I now becomes 4, and LT becomes 2. So now we are looking at this element, comparing that with the pivot R. They are the same, so I is simply incremented by 1, and so on and so on and so on. Right? And notice that once the while loop is done, the partitioning is done, and look at the 3 partitions. So we have a first partition whose elements are all smaller than the elements in the middle partition, and these elements are precisely equal to V. Okay, and then you have this partition whose elements are all greater than V, the pivot element, and these guys are all less than the pivot element. Okay, so that's how the partitioning works in quick 3-way sorting. Okay. So now what we want to do next is come up with a way of characterizing the number of duplicates that we have in an array. Okay, so can we come up with a quantitative way of characterizing the number of duplicates that an input array has? So let's say we are given n keys with k distinct key values, right? So the total number of keys that we have is n, and there are k distinct key values, right? Now for each I from 1 through k, we are going to define f sub I to be the frequency of the ith key. Okay, so we are saying that f sub I denotes the number of times the ith key appears in the input, right? And then the p sub I is simply going to be the probability that the ith key is found when a random entry of the array is sampled. And what is p sub I? P sub I is simply the number of times that the ith key shows up divided by the total number of keys, which is capital N. And that is clearly a probability, and what that probability says is that is the probability with which you will find that particular key value when a random entry from the array is sampled. Okay, so let me give you a concrete example of this. So let's say these are my different keys. So R, W, 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 and then B, B, and B. So how many keys do we have in total? Well, n is 2 plus 3, 5, 5 plus 3 is 8. And how many distinct keys do we have? We have 3 distinct keys. Okay. Now, what is the probability of the key R? Well, you have 2 for its frequency. There are 2 keys that have the value R divided by n, which is 8. That is a quarter. What about the probability of W? Well, that is 3 divided by 8 because you have 3 values that are W. So the probability of W is 3 over 8. And then what is the probability of B? Well, that is also 3 over 8. Okay. So what this means is that if you have a box with these 8 keys, and if you just reach into the box and pull an element out, the probability with which you will pull out an R is a quarter, and the probability with which you would pull out a W or a B is 3/8. So that's what we're saying here. All right. So now there is a measure called Shannon Entropy of the keys, which is a very famous measure from information content, and that is simply defined as shown here. Okay, so we denote Shannon Entropy, which is simply a number, as capital H, and it is computed using this expression. It's the negative of P1 log P1 plus P2 log P2 and so on, all the way up to Pk log Pk, right? Where these P sub i's are the probabilities of finding the ith key value, all right? Okay, and we can write it compactly using the sigma notation as the negative of the summation from I equals 1 through k of P sub I log P sub I. All right, so this formula here gives us a very nice measure of the information content of an array of keys. Okay, now you can very easily convince yourself that this value H is 0, and that's its minimum value when all the keys are identical. Okay, so when all the keys are the same, what is the probability of finding a key? Well, it is precisely 1, right? Because your entire array has just one key in it, so the probability of finding that key is 1. But what is the log of 1? It's 0. So the minimum value for H is 0, and that happens when all the keys are identical. And what is the maximum value? Well, the maximum value is log n, and that happens when all the keys are distinct. So that's another extreme. So one extreme is when all the keys are the same, in which case Shannon's entropy is identically 0. And the other extreme is all the elements are distinct, in which case the probability of finding each element, Pi, is 1 over n. And if you plug that into this expression, and you will see that H is log of n. All right, so H is greater than or equal to 0, and it's less than or equal to ln of n. All right. Now, in the previous lecture, we said that no comparison-based sorting algorithm can guarantee to sort algorithms with fewer than n log n comparisons, right? So we can state the same result using this idea of Shannon's entropy, right? So we can say that no comparison-based sorting algorithm can guarantee to sort n items with fewer than n times h minus n comparisons, right? Where h is this Shannon's entropy, all right? So this is just another way of expressing that result. Now, the three-way quicksort algorithm that we just discussed as a modification as an improvement over the standard quicksort algorithm, it uses approximately n times h comparisons to sort an array of n items, okay? Where h is given by this formula, that's the Shannon's entropy. And notice that h, since it is greater than or equal to 0 and less than or equal to log n, when you have many duplicates in your input array, then h is very close to 0, right? Because that's what we said before. So in that case, the running time of three-way quicksort is very close to linear, right? And on the other side, the other extreme is when there are very few duplicates in your array, in which case Shannon's entropy is closer to log of n, and the running time of three-way quicksort is approximately n log n. Okay, so what we are saying here is that when your input array has lots of duplicates in it, then three-way quicksort works really well, and it gives you roughly linear time performance. All right? And whereas if your input array has very few or no duplicates, then it sort of reduces to the standard quicksort algorithm, and it becomes a linearitmic algorithm, an n log n algorithm. Okay, so the running time of quicksort, of three-way quicksort, is greater than or equal to, let's say, approximately n, and less than or equal to n log n. Okay, and on this side we have many duplicates, and on this side you have few or no duplicates. Okay, so that's basically the running time of three-way quicksort. Right? So three-way quicksort does really well when you have an input array that has a lot of duplicates in it. Okay, finally let's compare the quicksort algorithm with some of the other sorting algorithms that we've discussed so far. So we use the sort compare program that we talked about before, and here we are showing a comparison of quicksort versus selection sort on an input of size 10,000. So we are trying to sort 10,000 random doubles here. Okay, and the output suggests that quicksort is about 30 times faster than selection sort, and that makes sense because selection sort, after all, is a quadratic time sorting algorithm, whereas quicksort is linearitmic. Here is a comparison of quicksort with insertion sort on 10,000 random doubles, and here again quicksort is about 30 times faster than insertion sort. Again, it makes perfect sense. This guy here is quadratic, whereas quicksort is linearitmic. Here is a comparison of quicksort and shell sort on an input of 10,000 random doubles. So here notice that the performance of the two sorting algorithms is quite comparable. Okay, and that also makes sense because we know that a shell sort is quite efficient. I mean, we don't have a mathematical formula for its running time in the average case, but it's in the linearitmic ballpark. Okay, and hence the performance of quick and shell are quite comparable. What about quick and merge? The same thing. They are both quite comparable, and that makes sense because both are linearitmic algorithms. And finally, here's a comparison of quicksort and the system sort of Java. And this output is suggesting that quicksort is somewhat faster than the system sort. But this number is fairly low, so we don't really want to make any big conclusions from this number here. All right? Okay, so so quicksort and merge sort are fairly efficient, and they both belong to the linearitmic class of algorithms. And they're also optimal. That's the best that you can do. All right? So that concludes this lecture on the quicksort sorting algorithm. Thank you for your time.